So, black holes. Black holes are a point of incredible mass, of infinite density, that cause infinite curvature in space-time. This has great properties, including the event horizon, which is a point around this curvature which nothing can escape, including light. So light can't escape out of the event horizon, meaning it's a black hole. It's basically just a point of incredible mass, incredible density that bends curve space-time to the point where nothing can escape inside the event horizon. Will, how do they form?
So essentially, there's quite a large set of like parameters that have to be fulfilled for a black hole to form. So they usually form from stars of above 9 solar masses, so 9 times the mass of our sun. And these, because they have a far higher mass, they use up their hydrogen fuel in the fusion reaction to form helium far faster and burn hotter in their shorter lifespan. Uh, as this hydrogen fuel is used up, the star begins to fuse heavier and heavier elements until it reaches iron 56 or sometimes nickel 56. And these elements can't be fused as if they were going to be fused, it would need an input of energy, and that reaction would be endothermic rather than exothermic, which is what the star needs to, I guess, be a star.
Yeah.
So, because of this, the inward force of the weight of the star is no longer balanced by the fusion pressure, which acts outwards from the center. So the balance temporarily slips in the weight's favor, and the star collapses in on itself, releasing energy in the form of neutrinos. And the rest of the star explodes outwards, releasing the heavy elements which were used to form like planets and other celestial objects. From roughly 9 to 20 solar masses, where the fusion eventually wins, the core forms a neutron star, which is essentially an extremely dense atomic nucleus, the size of, say, a city. More than 20 solar masses, it typically forms a black hole.
Sure, yeah, because when it like loses that outward fusion pressure, it has like this supernova, this explosion that forces it to compress into a black hole because it sort of compresses the core. Are you done with
Yeah.
formation? Sure. Okay. Features. There's a lot of cool features of black holes. How do we observe black holes? So there are these things called accretion disks. These are disks around the black hole where matter orbits very fast, becomes very hot, and the friction and collisions between this matter orbiting a black hole, it radiates light. So that's how we spot them. If you see photos of black holes, it's like this black sphere with these sort of orange and white rings around them. Light also orbits the black hole, so if you were close to a black hole, you see a reflection of yourself as light just goes straight around it. If you were to fall into a black hole, you'd be spaghettified, as the gravitational force on your toes is a lot more than your head, so you sort of just string out into a long line of atoms and plasma as you sort of fall into the black hole. The singularity. Now, singularity is a main point of black holes. It's the center of the black hole. It's where all the mass is crushed to. If you fall into a black hole, you just fall into the singularity. Properties of black holes. Black holes have mass, spin, and charge. That's it, because which means that all singularities are roughly identical, because all the matter is crushed down without any memory of what it used to be. So all singularities are identical. All they change in is mass, spin, and charge. Black holes cannot be described by general relativity. They're sort of at the very limits of our understanding of physics, and they sort of seem to break a little bit of what we know. I mean, they are sort of understood by it, but we need greater physics to be able to understand them. Generally, most of our maths is easier when black holes don't spin. What we learn about them is when they're Schwarzschild black hole, one that doesn't spin. But actually, most of them do spin up to 90% of the speed of light, because when the dying stars, the giant stars that were compressed into black holes, they were spinning great speeds when they died. This means that singularity also spins, becoming a ring singularity, or being called a ringularity, which is a dumb name, creating an ergosphere, so it bends space-time into this weird shape called an ergosphere outside the event horizon. Yeah, that's about it for features. Do you want to explain Hawking radiation?
So essentially, in empty space, even where there is no matter, say in the vacuum of space, quantum fluctuations occur basically all the time, which is where particle and antiparticle pairs are forming, splitting apart, and then annihilating each other.
Yeah.
So they don't form any actual matter. But when this happens near or on the event horizon of an actual black hole, one of the antiparticle-particle pair may fall into the black hole, while the other escapes to infinity, boosted by the mass and gravity of the black hole manifesting itself as a photon. And this takes mass from the black hole, which at the start basically is an infinitesimally small amount of mass by which the black hole decreases. But as more Hawking radiation occurs over time, this rate increases. So eventually, probably hundreds of trillions of years into the future, black holes will start to essentially evaporate when all of their mass has been used up via Hawking radiation.
The rate of evaporation increases, which is kind of bad for galaxies and things, because you're at the centre holding it all together, so they start evaporating, so kind of go a bit badly. Alright, size of black holes. There's two ways to make a black hole. You can compress matter until it reaches the correct density. This is how most black holes are formed, because the supernovas sort of crush big stars, implode until they turn to a black hole. Or you can add matter to a black hole until it reaches a certain tipping point, where size is so great, its density is so great that it becomes a black hole. We can understand the size of black hole using the Schwarzschild radius, which is r equals 2gm over c squared. This is the radius between the singularity and the event horizon. Therefore, we find that the radius is dependent on it depends on mass. So you increase the mass of the black hole, increase the radius. So you can keep adding mass to something, and it will eventually reach its Schwarzschild radius. And that's generally, you can do some calculations with that. I think that's generally more for non-spinning black holes, as in the Schwarzschild black hole. I think things do get very complicated as soon as we get to spinning black holes. Especially with spinning black holes, things can orbit closer. There's a lot more complicated things going on. Anything to add, Will?
I think, well, there's a theoretical class of black hole that I was reading about called primordial black holes. And
primordial soup.
Yeah, and they formed from density fluctuations in the fledgling universe when near the start, near the black hole, near the Big Bang, and they're like the size of atomic nuclei. And due to Hawking radiation makes these seem improbable, because if they were to have a smaller mass than, say, a stellar black hole, then they would just evaporate super quickly. So they would need to have billions of kilograms of mass concentrated into the size of an atomic nucleus, which seems fairly improbable.
See, this is also slightly improbable.
And these are often theorized to be the so-called dark matter, but as of yet, nothing has been proved with them.
Yeah, I think that's about all I've got. You anything else, Will?
No, not really.
Sure, Mark. Cool. Nice.